Welcome. I'm Denton Ebel, Curator of Meteorites at the American Museum of Natural History. I'm a geologist by training. I'm joined today by Dr. Harold Connolly Jr. and Dr. Vicky Hamilton from the OSIRIS-REx mission. And our driver in open space is Marina Gemma.
Hello. Happy Asteroid Day.
We encourage people to put questions in the chat, which we will answer as many as we can. And I thank our team on chat. So what are you looking at here? What you're looking at is the solar system rendered in the open space visualization engine. This is a device, a program that obeys the laws of gravity. Everything you see in it is accurate, and it shows data from all of our space missions, our telescopes, the entire universe. It's an amazing thing. So you're seeing a rendering of the solar system at a particular day. Every planet is where it was at that particular time. And the planets are rotating around, of course, the sun. The outermost planet with a blue orbit trail, you're seeing the trails. The planets themselves are too small to see at this scale. And that blue orbit trail is the trail of the planet Neptune. The next planet inward, do you know what that one is? Uranus. And the next one inward has rings. That would be Saturn. And inside of Saturn, as we zoom closer, we see the orbit trail of Jupiter, which appears as a light color. And Jupiter, the biggest planet, is kind of the outside of the asteroid belt. As we go further in, we can just make out the orbits of Mars in red, Earth in blue, and Venus and Mercury inside of Earth's orbit. Now look at that. Look how the planets make a very smooth and sharp plane, a plane in that we call the ecliptic plane. So they all orbit in the same plane, more or less. And right now we're focusing on Mars and Jupiter. Mars is called the red planet, so we gave it a red trail. And between Mars and Jupiter, one might expect there'd be another planet, but no, there is a single dwarf planet between Mars and Jupiter called Ceres, which is the largest of a huge class of bodies called the asteroids. And what you see here is a new orbit trail in white between Mars and Jupiter. And that orbit trail is the trail of the asteroid Vesta. Vesta was discovered about over 100 years ago, and it was the fourth asteroid discovered. It is, however, the second largest of all the asteroids, and it accounts for about 9% of the total mass or weight of the asteroids in the asteroid belt. And here we're approaching Vesta on the evening side, if you will, where on one side the sun is lighting up half of Vesta and the other half is in darkness. Vesta rotates at 4 hours per rotation. So its day and its night are each 2 hours long. And what you can see on Vesta are many impact craters. Some are large and some are very small, because anything that hits Vesta, even a grain the size of a sesame seed, makes a crater. And Vesta's been around a long time. We can see a lot of craters, and it doesn't have any weather, it doesn't have any water, it doesn't have any plate tectonics, so nothing really changes that much on this asteroid. But Vesta represents a kind of asteroid that has a core and a crust. The crust is a lot like the crust of the Earth. And we see the impact craters, and we see on one side a giant impact where something big hit Vesta and a lot of material escaped, because Vesta is very small. It's about twice, its diameter is about twice the length of New Jersey, about 500 kilometers total. So when it got hit by other asteroids, the material from Vesta was ejected into space, and some of that material has made it to the Earth and has hit the Earth as meteorites. And we orbited Vesta with a mission called the Dawn mission. And that mission took a lot of images and looked at it very closely with cameras and infrared spectroscopy, and was able to really nail down that these rocks, and this is a meteorite called Johnstown, it fell in Colorado about 100 years ago. And this meteorite comes, we're pretty sure, came from the asteroid Vesta. And you can see it's a big chunk, and in it, it has green mineral grains and a fine-grained matrix, and then on the outside, it has a fusion crust. So this is characteristic of all meteorites, particularly stony meteorites like this one from Vesta. But these minerals that make up this rock are not similar to ones you'd find on the Earth, for example, on a beach in Hawaii or in Iceland. These are volcanic materials that are formed on the surfaces of planetary bodies, which have cores. So this material is similar to material you might even find on the Moon or on Mars. But most of the material in the asteroid belt is actually very primitive in the sense that it didn't ever come from a body like a planet. It's sort of like the leftovers of the formation of the solar system itself and the planets themselves and the sun. So now you see that thin plane in which all the planets orbit the sun. And when we look at the asteroids that are in the asteroid belt, the main belt of asteroids between Mars and Jupiter, we see that these bodies actually can go above and below the plane of the ecliptic, the plane of the planets. And so here we visualized the actual positions of many, many thousands of asteroids. We have about 800,000 asteroids in open space. These are the real orbits of these bodies through time. We can predict and we know where these bodies are, and they all obey the law of gravity, so we can tell where they're going to be. And so if we ever visit them with spacecraft, we need to know all those things. But if you were standing on one of these asteroids pictured here, you wouldn't be able to see with your naked eye another one. You'd have to use a big telescope. The asteroids are spaced out a lot because there's a lot of space out there. And even though there are a lot of asteroids, there's a lot of space. So when we send spacecraft outward past the asteroid belt to, say, Jupiter or to Saturn, we don't worry that much about hitting an asteroid. And because we know where most of them are, at least the big ones, we can actually plan how to make those journeys. So asteroids are made of different types of material. So in the inner asteroid belt, which is a brighter color in this image of the yellow bodies, the inner asteroid belt is more stony meteorites, stony asteroids, which are sources of stony meteorites, and metallic asteroids. We're actually going to be sending a spacecraft called the Psyche mission to a metal asteroid. And these, as we go further out in the asteroid belt, the asteroids become richer in carbon and in water or hydrogen that's bound to minerals in the surfaces of these bodies. And those are very interesting bodies because we think that the sources of some of the ice and water and organic molecules that make up human life and the oceans and our atmosphere may have come from asteroids hitting the Earth long, long ago. Now, what Marina has done here is turn on another class of asteroids that orbit in the orbit of Jupiter. These are called the Trojan asteroids, after the Trojan War of Greek mythology. One of the interesting things about the Trojan asteroids is they orbit around the sun with Jupiter, but they're 60 degrees ahead of them and 60 degrees behind Jupiter itself. And those are stable places which a man named Lagrange predicted there would be stuff there in 1774. That's the time of the Revolutionary War, the founding of the US. And it was only in 1906, more than 100 years later, that we actually discovered the first of these class of asteroids, the Trojan asteroids. And we think that these asteroids are covered with organic molecules, things like gasoline is an organic molecule, or tar that roads are made out of is an organic molecule. And that's the kind of molecule that we think covers these asteroids. So they're very rich in organics. So somebody asked, why is the belt somewhat triangular? Well, that's an interesting question. As we go farther out, and you can see this very well, how Marina has displayed this, as we go farther from the sun, the gravitational force of the sun is less. And so the asteroids are spread out more above and below the plane of the planets themselves. So it appears to be a sort of a flared disk. And we, in fact, think that the original solar system material before the planets formed was a disk of the same kind, where the inner parts are narrower and the outer parts, because of the energy of the interaction of the asteroids with each other and with Jupiter and Saturn, are spread out more. So these Trojan asteroids occupy spaces that we could think of as gravitational parking lots. Like the asteroid belt itself, these are stable orbits for the most part, where these objects can stay and just sit there for a very, very long time. Metal asteroids are made of iron and nickel metal primarily, but of course they also contain gold, platinum, cobalt, iridium, and these would be resources that we may someday mine if we end up learning how to mine space assets. So that was in response to a question from Mark. So how did the meteorite break off from Vesta? Vesta, V-E-S-T-A, was another question that came up in chat. So when these asteroids hit each other, which they occasionally do, they can break apart, and the bits and pieces of that collision, just like smashing two rocks together, can drift around the solar system. And some of them, due to the gravitational interaction with Jupiter, can actually go into the inner solar system. And the asteroids that come into the inner solar system can hit the Earth, can hit Mars, can hit Venus or Mercury even. And these are asteroids that are called potentially hazardous asteroids. So if we look at those asteroids, which are now shown in red, the near-Earth asteroids or potentially hazardous asteroids, we see that there's a lot of stuff out there in the solar system, and we haven't even shown you the comets, which are a different matter, and we haven't even shown what's going on near the Earth. Someone asked, why will the asteroids ever come together into something like a planet? As you can see in this view, Jupiter is on the outside of the asteroid belt. And Jupiter has a very strong gravitational field because Jupiter is a very big planet. And because of Jupiter's interaction with these rocks, they were never able to, nor will they, combine to form one planetary body. If they did, it would be about 5% the size of our own moon, a very small body. Most of the asteroids over the history of the solar system have been ejected from the solar system by Jupiter or thrown into the sun or the inner planets, again, through their interaction by Jupiter. And now, what are we doing here? We're fast forwarding. we're now moving at about 5 days per second. So you know every time the Earth goes around the sun is 1 year. So if we go 5 days per second, now we're going around the sun in 60 years instead of 365. So we are moving quite rapidly, but this is to show you the motion of the Earth, and we've increased the size of the Earth 100 times. And you can see Earth spinning here. Each day, the Earth spins once. And you can see how many asteroids there are that are near the Earth's orbit and across the Earth's orbit. Someone asked about an interstellar asteroid. We, in fact, in just the last couple of years, we've seen 2 interstellar asteroids because our ability to find things has gotten so good. And these were very strange bodies. Maybe we'll have a show about them coming up. So Earth is a small target. Isn't that a good thing? Here we've made the Earth 100 times larger than it really is. And space is also really big. So luckily, the Earth doesn't get hit that often by asteroids. It gets hit sometimes by meteorites that are small pieces of asteroids, and it occasionally gets hit by a large body. And in fact, today is Asteroid Day. And Asteroid Day was declared by the United Nations as June 30th each year to increase our awareness of these hazards, because we as humans need to discover how to protect the Earth from big asteroids like the one that did in the dinosaurs, or at least most of the dinosaurs. Did you know that the descendants of dinosaurs are represented today by birds? So there's some that did survive. So this gets to the question of why do we sample asteroids? We want to understand these rocks, and the reason why is not just because they may have delivered water and organic molecules to the inner planets, to the Earth, but in order to predict their future paths. So for each of these asteroids that crosses the Earth's surface, we want to be able to predict, using the laws of gravity, where these bodies are going to be 10, 50, 100 years from now. So we can think about how to protect the Earth if we need to move one of them out of its orbit so it doesn't hit us. And in order to do that, we have to understand what they're made of. How do they interact with sunlight? So the trails here that are red are those potentially hazardous asteroids. That's how we represent them. And their tails we are showing so that you can see them, because the asteroids themselves are very small. So predicting their future paths depends on how they interact with sunlight. Imagine something getting very hot on one side because it's facing the sun. And then as it rotates, that hot part moves around to the other side, and it emits that heat as energy. That is going to push the asteroid around. So the asteroids obey the laws of gravity, but they also have other forces working on them. And how those forces work on them depends on understanding what the asteroids are made out of. So that's why, to understand space rocks like this better, we launched the OSIRIS-REx mission September 8th of 2016. That's almost 4 years ago. We launched it to an asteroid. We didn't know the mass of the asteroid very well. We didn't know what it was made out of. So getting there and doing that is tricky business. So now I'm going to turn this discussion over to Dr. Harold Connolly and Dr. Vicky Hamilton, who will say a little bit about themselves and tell you about this exciting mission to return material from a carbon-rich, water-bearing asteroid. It doesn't have liquid water, but it has water bound to the rocks themselves.
Thank you, Dr. Ebel. Thank you very much. A wonderful introduction. I'm Harold C. Connolly, Jr. I'm the founding chair and professor of the Department of Geology at Rowan University, and I am the mission sample scientist for OSIRIS-REx, which means I am a member of the science team and part of the managerial team of the science team. And my role is focused on the sample, everything to do with analyzing and the origin and evolution of the sample we're going to bring home. As Dr. Ebel told you, OSIRIS-REx is an asteroid sample return mission. It is NASA's New Frontiers 3, the first NASA asteroid sample return mission, and we're all very excited. The spacecraft launched in September of 16, and exactly 100 milliseconds after t equals 0 was called. And as you can see on the first, or the left-hand slide, left-hand part of the slide is an actual picture taken by the United Launch Alliance, which is the launch company partnered with NASA to launch rockets. And on the right-hand side is a chance image that was taken by an astrophysicist, Jackie Flaherty's father, from the American Museum of Natural History, is where Jackie is located and works. And he happened to fly by the launch and took that image, which was purely by luck, which is a really exciting image to look at. So the launch took place from Kennedy Space Center, and we began our journey to asteroid Bennu in September of 16, which took essentially a little over 2 years to arrive at. And what does Bennu actually look like? We were really excited and had some thoughts about what we might see when we arrived at the asteroid, but our expectations were blown out of the water. We didn't expect to see this beautiful object in space that looks like a top with lots of rocky material all over it. And as you can also see, as Dr. Ebel discussed about Vesta, you can see the impact. There's impact craters on the surface of the asteroid, very similar to Vesta or the moon. And as was explained, that's because asteroid Bennu is an airless body, and it has no water, no wind, no plate tectonics to change the surface, which has happened on Earth. Now, keep your eye on that little red arrow that's pointing to a large boulder, which is known as Bennu. And that's an official feature name for that boulder. And we're going to take this image, which was taken by the spacecraft on the approach phase, and flatten it out, just like a map we would use here on Earth to get somewhere. The arrow again is pointing to the boulder Bennu. Bennu for scale is 12 stories high. That is really a large boulder. It's not small. And as you can see along the equator in the center of the map, this beautiful black and white image, are lots of impacts, lots of craters, impact craters along that equator. The differences in grayscale that you see, or black and white color differences, represent real compositional differences of the boulder. So the asteroid is actually not the same material. It is composed of multiple material. And a question from Julie is, why isn't Bennu round? Well, Bennu actually is a rubble pile asteroid. When it was once living as its parent body, or its previous generation of asteroid in the asteroid belt that Dr. Ebel pointed out, it actually was involved in a collision, which broke it apart. It was reassembled and moved out of the asteroid belt to become in a Earth-crossing orbit. And one of the many reasons OSIRIS-REx is going to Bennu to collect sample is so that we can better understand the composition and thus better understand how asteroids move. Asteroids are really time capsules, treasure boxes of 4.56 billion years ago. So by collecting a sample, there are many things we can learn about the early solar system as well. So what is the actual size of Bennu? It's kind of difficult to get a feel for something in space when it's all by itself. So what is the actual size of Bennu? And that is something that is relative to, as you can see on the slide here, relative to the Empire State Building and the Eiffel Tower. And as you can see, the asteroid Bennu is just slightly bigger than the Empire State Building, which many of us in New York City, of course, are very familiar with, which is in Midtown Manhattan. So the asteroid is big, but it's not huge. It's not like Vesta, as Dr. Ebel pointed out. And that gives us an opportunity to also navigate around something very small, which is the first time that a spacecraft has navigated around something as small as Bennu. So, question now is, what's the relative size of the spacecraft to the asteroid itself? And for that, I'm going to turn it over to Dr. Hamilton, who will discuss that. And before I do that, there's one question from Victoria that says, can asteroids have moons? Yes, they can, and they do.
Okay, thank you very much, Harold. Hi, everybody. Thank you for joining us today. My name is Vicky Hamilton. I'm a geologist by training. I'm also a member of the OSIRIS-REx science team. I'm the mission spectroscopy scientist. And so what that means is that I study the rocks and the minerals and what they're made out of on the surface of Bennu. I'm going to tell you a little bit more about OSIRIS-REx. So what you see is a picture of our spacecraft right before we put it into the object on the back right there. That big white cone is called a fairing. It is what will be on the top of the rocket that launched OSIRIS-REx to Bennu. So if I take your eyes back to the left-hand side of this picture, you'll see a man standing there in a blue suit. Now, he's there partly to show you just exactly what is the size of the spacecraft relative to something that you can recognize. And you'll notice that he's wearing a blue bunny suit, or a bunny suit is what we call it. Now, we might think that that suit is to protect him, but in fact, it's really there to protect the spacecraft. Because we want to measure things like organics and water on Bennu, and we're going to be collecting a sample that contains those compounds, we don't want the spacecraft to be contaminated with those things from Earth. So he wears the bunny suit in order to protect the spacecraft and help keep it clean. So if you look at the spacecraft, you'll see that big silver cone pointing towards the man. That's the antenna. That is how we communicate with the spacecraft and how it sends data back to us. On the left and right-hand sides of the spacecraft are big black square panels. Those panels are solar panels, and they're just like the solar panels on people's houses. They take solar energy and convert it into power. And that power charges the batteries on our spacecraft, and those batteries then power the instruments and the antenna. At the bottom of the spacecraft is where the main engine sits, and that's our source of energy for actually getting out to Bennu and getting back. And so finally, I'll call your attention again back to that big white cone in the background. This picture was taken right before the spacecraft was put into that cone to be launched at Bennu. And so one of the questions we have is where we're going to collect a sample to bring back to the Earth. And so part of this mission is not just to send a spacecraft to Bennu and survey Bennu and understand its mineralogy, but it is also to collect a sample that we will bring back. And so in a moment, we'll watch an animation that was provided by our Canadian colleagues. OSIRIS-REx is an international mission, and so some of our team members are in Canada, and they created this particular animation that shows the 4 places that we've considered sampling on Bennu. And so the animation will show you those sites in sequence. And it's going to show you some circles here that are marked as being 10 meters in diameter. That's about 33 feet across. And that's the circle in which the spacecraft has to actually target to collect a sample safely without damaging the spacecraft, because you can see there's a lot of really big rocks around. And so we need to avoid those. They're considered hazardous to the spacecraft. And so that's how we develop a location from which we will collect a sample. So what we're going to do is take a look at our top site next. It's called Nightingale. And now you can see Nightingale there. And the little black rectangle with the blue outline and the white X is our spacecraft. It's a representation of the size of our spacecraft as it's contacting Bennu. Now, it's important to remember that we don't actually land on Bennu. We just touch it with our long robot arm. But to give you another sense of scale, something else you might relate to a little more easily, off to the side there is a little cartoon of a car in a parking lot. And so that gives you a sense of just how small this place is that we're collecting a sample. So we have to have a very specific device to collect a sample. So how are we going to actually get that sample? I said we're going to touch the surface, but the actual collection of it relies on a fairly sophisticated device. So the device that we're going to use was developed by our colleagues at a company called Lockheed Martin. And that company developed this device that we call the touch and go sample acquisition mechanism. Now, that's a really big mouthful of words, and so we just call it TAGSAM for short. Now, again, we have a man in a bunny suit here. Again, for the same reasons, we're protecting the spacecraft equipment from contamination by human compounds, the organics that make us up and that we shed all of the time. So that arm, you don't see quite all of it in this picture, but the arm over his head has multiple joints, just like our arms do, elbows and wrists. And that arm is about 11 feet long. Now, the part that will touch Bennu and collect the sample is that round object in the plastic bag down at the far right-hand side of the picture. And if you go just a little bit to the left of that and in sort of near the middle of the picture, you'll see lying horizontally a couple of silver oblong canisters. And those canisters contain dry nitrogen gas that we will use to stir up the surface of Bennu so that little rocks and pebbles and sand grains go into the sampling head that, again, is down at the right in the plastic bag. Anne-Marie asks if we can live on an asteroid. Right now, that would be a pretty tough proposition. Asteroids don't really have a lot of natural resources. It would be hard to get water. You'd have to carry it with you, and you can't really do that for a long time. But, you know, never say never. There's always the possibility that with some of the larger asteroids in the solar system, we might be able to have human habitation sometime in the distant future. So now I'm going to show you another example of how OSIRIS-REx will collect a sample. And this will show how the spacecraft approaches the asteroid and contacts it. So again, I'll reiterate that we don't actually land on the asteroid, we just touch it. And we back away very, very quickly, and that is to avoid damaging the spacecraft. So you can see that arm reaching out. Again, that's about 11 feet long. You can see that round sampling head. And here we touch the asteroid and back away. And hopefully now we have our sample. And once we have collected the sample, then we have to stow it and all of that. But the first thing we have to do is explain how the collector works. And so for that, we'll have another animation, and that will talk about how TAGSAM works in detail. Now, I mentioned that we have gas canisters, and those stir up the surface. In just a minute, we'll see how that works. And basically, you're going to see what looks like the outside of the TAGSAM head contact the surface, and now you see the arrows showing where the gas is going, and the sample canister filling up with the disturbed sand and pebbles and little bits of rock. Now, I'll let this play through one more time just so you can see it. But then the question is, okay, so we collect our sample and we back away from the asteroid. What do we do next? And the next thing we have to do is prepare that sample for the return journey to Earth. We can't just leave that big robot arm hanging out in space while we fly back to the Earth. And so we want to make sure, and we also can't deliver the whole spacecraft back to the Earth. So we have to prepare the sample to be carried back on the journey to Earth, which will take another couple of years. And so to do that, we store it in a container, a capsule. We call this the sample return capsule. We pop the TAGSAM head in there, the arm lets it go and folds away, and then the sample canister closes for the return journey to Earth. And so after we get this part of the processing done, then we start the journey back to Earth. And I'm going to throw things back to Dr. Connolly to talk about what happens at that point. Harold?
Thank you, Dr. Hamilton. Appreciate it very much. After we stow the TAGSAM head rich with our sample, we begin the final part of OSIRIS-REx journey, which is back to Earth. It releases a sample return capsule to Earth, goes through the atmosphere, the sample, precious sample inside. You'll see a parachute in a moment. A parachute opens up, and the sample return capsule gently lands in the desert of Utah, where myself and several other members of the team, including Dr. Hamilton, curators from Johnson Space Center, NASA's Johnson Space Center, will retrieve the sample return capsule from the Utah desert, of course, with people like the PI of the space mission as well, Dante Loretta, and we will prepare that canister for shipping to NASA's Johnson Space Center. It goes to the curation facility, where in a very sterile and clean environment, the canister is opened up for the first time after returning to Earth in September of 2023. Remember, this mission launched in December of 2016 and was selected in May of 2011. It's a long mission. I started on the mission in 2008, and I think Dr. Hamilton even started before me. Once that sample is opened up, and a few of us in that room looking at the sample for the first time, we will then begin our analysis process of the return sample to meet our scientific goals and understand the treasures that Bennu has held for 4.5 billion years. And over a 2-year period, we will be investigating, analyzing the sample, and releasing our data to the scientific community and the general public, which will be really an exciting time period. It's an intense time period, and it's the final goal and prize, if you will, of the OSIRIS-REx mission. So I want to thank you all very much. This has been a great honor for myself, for Dr. Hamilton and Dr. Ebel. Thank you so much for inviting us, and everyone at American Museum of Natural History, where I've been associated for many, many years. And I wish you all a happy Asteroid Day, and be healthy.
Thank you, Dr. Connolly. And thank you all you who attended our presentation. And thanks for your great questions, which I had the ability to answer some of most recently. Do keep an eye out for the upcoming American Museum of Natural History events. Tomorrow we have a Sci Cafe about spiders. And on Thursday, we have a Scientist at Home presentation about rocks and minerals. And please, when you sign out, you will see a survey. Please fill it out to help us do better next time. And thanks everyone for attending. Thank you, Marina, for driving open space so wonderfully. And thanks to the team at the museum who made this happen. Thank you very much.